So here we go. Probably this is tied for my favorite unit. Again, the combinatorics and the probability sections are why I pushed hard already 3 years ago to teach Foundations of Math 12. They couldn't fit it into my timetable 3 years ago, but they did last year. Last year I used the textbook. The textbook did a terrible job. This does a much better job. Review. Here's the problem with probability. Logan, all of you have a basic gut instinct for probability, which is right. All of you are wrong as soon as we get anything even remotely barely complicated. Humans are terrible at figuring out odds. It's why we're so superstitious. It's why we're so superstitious. Basics we're good on. So you ready? Read along with me. A fair die is rolled. By the way, I'm a grammar nut. 1 die, like Brendan rolled. 2 dice. Dice is plural, die is singular. So not only do you roll a die, if you're sitting in a small chair, you feel like you want to die, but that's a whole other issue. This is 1 die. What's the probability of rolling a 1? You all know this. 1 in 6. See, I said you all have a basic understanding. Stop, don't write that down yet. I want to give you some notation. What would be a good abbreviation to use for the word probability? What would be a good abbreviation to use for the word probability? We're going to use a capital P. And then in brackets, we're going to write the event. In this case, a 1 is 1 out of 6. That's what we're going to use. That, Rachel, is our maximum explanation for minimum writing, but clarity, you know, same as I do in physics. I want to be crystal clear, but as little writing as possible. A circular spinner is divided into 4 equal sectors. I guess we're thinking kind of like that. Labeled clubs, diamonds, hearts, and spades. When it's spun, what's the probability that it lands on hearts? You all know this one too. 1 out of 4. Probability of H, 1 out of 4. One coin, this is not what the question C says. 1 coin is tossed. What's the probability of getting a head? 1 out of 2. 2 coins are tossed. What's the probability of getting 2 heads? Now the question became, and I barely made it more difficult, but now you're guessing. Now you're guessing. So we're going to come back to C. By the way, we would write it this way. Probability of, I would probably go heads on the first, comma, heads on the second, comma, equals. It says don't calculate the probabilities at this time. We did the first 2. Some terminology. So probability, actually, the story behind probability is as follows. About 300 years ago, a mathematician had a friend who was a nobleman. And the nobleman loved to gamble, play cards for money. And as he was gambling with his friend, he was winning, but hadn't yet won, and they got interrupted and the game had to end. And so he wrote the mathematician, who was Fermat, and he said, look, could you tell me mathematically what would be the fairest way to split up the pot? Should I get all of it? Because I was winning, but I hadn't won yet. I still might have lost. Can you come up with a mathematical way so that my friend can agree that we've split the money up fairly? And over this exchange of letters came the entire mathematical branch of probability. There's a reason why I keep going back to gambling. It's where it started. The problem with probability is it has no power. It has no power. Just because the odds of rolling a 1 is only 1 in 6, I can still roll a 1. I can still beat those odds. But what it can do, Kyle, is be a guideline to help you make the best decisions over time. If you keep going with the best probabilities, over the long term, the more you play, the better you'll do. Probability theory, it says, deals with the mathematics of chance or prediction. Here is some terminology. A trial is any operation whose outcome cannot be predicted with certainty. Flip a coin. Roll a die, pick a card. An experiment consists of actually doing one or more trials. A coin is tossed, 2 dice are rolled. A coin is tossed and a dice are rolled. 5 cards are picked. An outcome is the result of carrying out an experiment. So the experiment is rolling a die. The outcome for Brendan, when he walked in, was, what did he roll? 2. Okay, there's our outcome. The sample space, often symbolized with a capital S for sample space, is a set of all the possible outcomes. For example, if you're flipping a coin, what are your possible outcomes? More specific. So the sample space for a coin, H, T. We'll use abbreviations quite a bit. The sample space for rolling 2 dice would be 1 followed by a 1, 1 followed by a 2, 1 and 3, 1 and 4, 1 and 5, 2 and 1, 2 and 2, 2 and 3, 2, all the way up to 6 and 1, 6 and 2, 6, all the way up to 6 and 6. Those are all the possible outcomes for rolling 2 dice. For flipping a coin and rolling a dice, you can get heads and a 1, heads and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6. Tails and a 1, tails and a 2, tails and a 3. And sometimes we'll write out the entire sample space. Sometimes you'll notice we'll go ... and we'll say spot the pattern. An event is a subset of the sample space. So what did you say, Dom, the sample space for flipping a coin was? No, the sample space. What are the possible outcomes? The event would be, you got a tail. That's the event. Or what's the sample space for a deck of cards? The entire deck of cards. The event would be, I had my deck of cards, there it is. So sample space, I could write out the entire deck of cards. Am I going to, and I'm just going to call it a deck of cards, and I'm going to assume, Brianna, since we also used them last unit, that you'll know what we're talking about. And the event is, I got a, what? Jack of hearts. There's the event. To denote the probability of an event A, we're going to use a capital P for the word, for the abbreviation probability, and then we'll write the event in brackets, often using an abbreviation. So I used H for hearts, I'll use H for heads if it's a coin, I'll use C for clubs, etc. Probabilities are usually represented by decimals or fractions between 0 and 1 because they're percentages. If something is guaranteed, what percent probability does it have to happen? 100%. What's 100% as a decimal? Remember your math 8? 1, right? If something can't happen, what percent chance does it have of happening? 0%. And what's 0% as a decimal? Still 0. All probabilities are going to be decimals or fraction between 0 and 1, but they can be equal to 0 or equal to 1. In other words, Mackenzie, if you're working out an equation and you get a probability of 1.6 bigger than 1, you've messed up somewhere because you're saying it's guaranteed to happen and guaranteed to happen somehow more than once at the same time. Yeah. If it can't happen, if it's impossible, we write the probability is 0. So for example, what's the probability of me rolling a 9? Come on. 0. What's the probability of me getting a 15? 0. No 15s in a deck of cards. What's the probability of me flipping a coin and having it balance on the edge when it lands? Not quite 0. I'm sure it's happened in history where the coin has bounced and balanced on the edge, but for the math purposes, we're going to pretend it's 0. When you flip a coin, we're going to say it's either heads or it's tails. No, we're not going to accidentally balance on the edge. I always have some smart aleck kid ask me that one, so I thought I'd shoot that one down right now. Okay? Oh, if the probability of something not happening is 0, what's the probability of something being guaranteed? I already kind of told you. 100%, or as a decimal, 1. If you ever see that, what they're saying is this has to happen. It's guaranteed. Oh, let me give you an example. What's the probability that I roll a natural number less than 7? In other words, what's the probability that I roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6? 1. It's guaranteed. Well, couldn't the dice end up balancing on its? No, I've already dealt with that. None of that. Okay. Next page. Here is the first rule. Oh, you guys get a formula sheet. Here is the first rule. Now, I'm going to give it to you as a formula, and then I'm going to give it to you as an English version. It says this. If an experiment has a set of equally likely possible outcomes. Now, this is going to become important later on, so we're going to underline the phrase equally likely, even though right now that won't mean much to you. Then the probability of event A is, you know what? It's the number of successes divided by the total number of outcomes. It's the number of wins divided by the total number of ways to play. It's, you know, the rule for probability, Sterling, is if you can count it, you can solve it. If you can count it, you can solve it. So if we go more formal than we did at the beginning, where I asked you to do questions intuitively, it says, consider the first two examples. A fair die is rolled. What's the probability of rolling a 1? Really, what you did intuitively is you said, the sample space for rolling a die is 1, 2, ... 5, 6. How many outcomes are there in the sample space? A grand total of 6 for a dice. I only wrote 4 of them. Spot the pattern, Carm. There's 6 grand total. So part 2 says, what are the favorable outcomes? 1. Are the outcomes equally likely? Yep, it's not a weighted die. So we're just going to write the word yes. And so the probability of rolling a 1, how many 1s are there in the sample space? Over. How many are there in the sample space grand total? That's the official definition of probability. The total number of favorable outcomes, wins, divided by the total number of possible outcomes. I'm not going to do B. What if instead, don't write this down, just watch. What if I said, what is the probability of rolling a odd number? How many odd numbers are there in the sample space? 3 out of 6. 3 out of 6. We are usually, Rachel, not going to reduce our fractions. You'll reduce them to check your answers in the back of the book, but I find that 3 out of 6 much more informative than 1/2, because the 3 out of 6 tells me, oh, there were 3 favorable outcomes out of a total of 6. I kind of like that. It helps figure out where the original question comes from. Complementary events. When the spinner this bad boy, hearts, clubs, diamonds, and spades, is spun, the sample space consists of 4 outcomes. There they are. The event lands on hearts is this one. The event lands on hearts is that one. What was the probability of that occurring? 1 out of 4. What's the probability that we don't get a heart? 3 out of 4. We call that the complement. Oh, we've already looked at complement both in logic and reasoning and in the last unit. So that's also why we tend to do these in this order. They build on each other. So the probability, hey, I have that handy notation. That's not hearts. Is 3 out of 4. So the event does not land on hearts is the complement of lands on hearts. We've seen that word before, and hopefully it's reinforcing what we've done both in logic and reasoning and what we've done in combinatorics. They're called complementary events. And it turns out, this is important, put a star next to this, the probability of an event and the probability of its complement add to 1. In English, here's what we're saying. Something happens or it doesn't every time. You are always guaranteed that an event happens or it doesn't. And guaranteed means adds to 1. That may not sound profound. That's hugely useful because often we're going to find it's easier to find the probability that something can't occur and then go 1 minus that to find the probability that something can occur. So, the complement of an event A is a set of outcomes in the sample space that are not included, and it's denoted as A apostrophe, which is read as A prime, or A with a bar over it. In fact, that's how I was taught, and I may fall back on that if I'm doing this absent-mindedly. In the old Principles of Math 12 course, not was done with a horizontal bar. But in set theory, not is prime apostrophe. So I'll try and be consistent using the apostrophe, but you may see occasionally I use a bar. And, key idea, the probability of something occurring plus the probability of something not occurring is guaranteed. Adds to 1. Okay? In other words, you either roll a 1 or you don't. Guaranteed. You either pick a jack of hearts or you don't. Guaranteed. How many cards are there in a deck? What was the probability of me getting that jack of hearts? What was the probability of me not getting that jack of hearts? 51 out of 52. I hope you didn't count. I hope you realized it was easier to go 1 minus and figure out the 51. Like I said, sometimes it's going to be way easier to figure out the odds of something occurring and subtract. Turn the page. Compound events. Events formed from repeated trials or from a combination of simple events are called compound. Like I said, lots of terminology today. Often a table or a chart or a tree diagram is useful. So consider the one that we didn't do, part C. 2 coins are tossed and the number of heads is counted. What's the probability of obtaining 2 heads? Tyler lists the sample space as 2 heads, 1 head and 1 tail, 2 tails, and the favorable outcome as 2 heads. This is wrong. This is incorrect. You see, Tyler thinks, oh, you have 1 way to get 2 heads out of 3, and so he says the probability is 1/3. This is incorrect. It's not 1/3. I like to use a tree diagram. So you ready? Down here is a tree diagram. Here's the first coin. What can we get? Heads or tails? Then, after I flip the first coin, I can get heads or tails, heads or tails. If I walk down each branch, Chelsea, it's heads, heads. This branch is heads, tails. This branch is tails, heads. This branch is tails, tails. So here's my question. How many of those are heads, heads? Put a little check mark right there. The probability of heads, heads is how many successful outcomes? Out of how many total outcomes? Not 3, 4. The nice thing about a tree diagram is once you have it drawn, you can answer any questions. Hey, what's the probability of 2 tails? One out of 4. What's the probability of getting 1 of each? See it? Jordan, what? Remember I said if you can count it, you can solve it. Okay? Hey, Did we just finish a unit on tricks to count without actually counting? That's why we always do combinatorics before we do probability. Is that okay? Okay. Yeah, I noticed. Turn the page. How much more are we doing here, Mr.? Oh, almost done. Good, 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 good. I like using trees. In fact, if drawing a blank, Scrabble bag, and buckets were some of the best tools that I could give you in the last unit, my fallback here is usually a tree, not a formula. Now, I've worked through some of the lessons, and the workbook is going to emphasize the formula, so I'm going to follow the workbook's approach, but I'll also try and show you my preferred method, which is trees. Did you have a question or a hand up?
Yeah, if you like trees, then why did you avoid it earlier on?
They're not that useful in combinatorics. They're not. They're hugely useful in probability. And give me till the second week of January, and I'll convince you why, and you'll agree with me. Okay? So, consider the experiment of spinning an equally spaced triangular spinner numbered 1, 2, 3, and 2 coins. Okay. I guess here is the tree diagram that we would start out. We would say, on the first event, you're spinning a spinner. What can you get? What are the possible outcomes? 1 or 2 or 3. So that's where these came from. Don't circle them, but just to show you that's where they came from. Then on the first coin, I can get heads or a tail. So you could get a 1 and a heads or tail. A 2, what would I put right here? We're going to fill this in. Heads or tail. 3, heads or tail. Then on the second coin, what are my possible outcomes? The same. Heads or? So I can go heads, tail, heads, tail, heads, tail, heads, tail, heads, tail, heads, tail. Now, Giancarlo asked a question about trees. Giancarlo, I love trees, except I won't use them for more than 3 events because they get too unwieldy. Even this is my borderline. Here, I might try and find a shortcut. But for 2 events, trees are great. Outcome. Okay. You know what? Instead of writing them out, can you just see them by walking down the branch? This is 1HH. This is 1HT. This is 1TH. This is 3HH, 3TH. Can you see that okay, Brianna? I'm not going to write them out. I'm going to say we can follow them. So it says complete the tree diagram. Check. How many elements are there in the sample space? How many branches do I have on the very, very final row? Count. Because if you can count it, you can solve it. 12? Could I have used the fundamental counting principle to figure that out? How many choices do I have for a spinner? 3. How many choices do I have for a coin outcome? 2. And how many choices do I have for another coin outcome? 2. There's the 12. And we'll start using the fundamental and the combinatorial. We'll start using that eventually too. But for now, we can count. 12. 12. C says show, oh, there. C says show how you can use the fundamental counting principle. Rachel, it's 3 spinner outcomes, 2 coin outcomes, 2 coin outcomes. Are all of these equally likely? Is the coin, does it say that the coin is rigged at all? So each of those is 50-50, half-half. Does it say the spinner is equally spaced? Each branch is equally likely. Okay. What's the probability of getting a 3 and 2 heads? That would be that branch right there. Any other branches? Nope. The probability of 3HH, how many successes? Out of how many outcomes? 12. A prime number and exactly 1 tail. Okay, I'm going to scribble out this check mark and I'll even change colors. 1, 2, and 3, which of those are prime? 1 is not prime. 2 and 3 are. Okay? Prime numbers, by the way, are defined as numbers bigger than 1 for which only themselves and 1 go into it. So 2, 3, okay. So I'm already in the bottom chunk. It says prime number and what?
Exactly.
So I'm going to walk down the branches. I'm just going to put a check mark. I guess this one satisfies that. This one satisfies that. Does the one beneath satisfy that? No. How many tails on this branch?
2.
Okay. What about the next? No. This one satisfies that. This one satisfies that. Probability of prime and a tail. How many successful outcomes? 4 out of 12, which I know is 1 out of 3, but I'm not going to reduce. I like example 3, I like example 3, I like example 3.
Example 3 give me on the test?
I'm going to give you a 2 dice question on the test, and for any 2 dice question, probably your best bet is to use a chart sample space. To very, very quickly write out the numbers 1 through 6 in the top row, write out numbers 1 through 6 on the left-hand column, and then in here, we're going to fill this in really quickly. It's going to take a couple of minutes. Is that in here? That's outside? Okay. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. What's the next row going to be? 2, 1, 2, 2. That's in the hallway, is that right?
Yes, in the hallway.
Okay. Deal with the distraction. Fill in the chart. It may seem like it takes you a long time. It's really about 20 seconds to make one of these, especially if I stop talking. Especially if I don't make a mistake. 4, 3, 4, 4. And when you're done, look up. So tree, I use that for cards. I use that for coins. By the way, can you see why I wouldn't really want to do a tree for 2 dice? Because from the first, I'd have 6 outcomes, and from each of those, I'd have 6 more outcomes. That would be 6 branches, and each one would have, it'd be very unwieldy to try and draw, Carson. By the way, how many outcomes are there in this sample space? Could you figure that out using the fundamental counting principle? Yes, but okay. 36. It says part C, list the event the same number appears on each die. You know what? I'm going to circle that. I think that is, you can circle this with your pencil, right there. If I wanted to, I could list it. It would be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. There. Okay. If you can count it, you can solve it. So D part 1 says, what's the probability that the same number appears on both dice? Probability of, how about we write the word same. Do we have an abbreviation for the word number in our English language? What? Oh, a lovely little number symbol. I'll figure that out if you use it. Can anybody see the answer here? What's the probability of, by the way, when you play a game, a board game, what do you call it when you roll the same number? It begins with the letter D. Okay, doubles, right? Is it still called that, I think? You guys have all played Monopoly. Okay, what's the probability of getting doubles? 6 out of 36. If you can count it, you can solve it. Without counting, what's the probability of not getting doubles? Please don't count them. Can you figure it out by using the complement? I heard it. 30 out of 36. So probability of, oh, same number apostrophe, not the same number. That's a short way to write different number. 30 out of 36. E says, how can the answer for D be determined? You did it that way, Mackenzie. You actually didn't, you didn't count all 30, did you? Okay. Oh, hey, what else could I ask? Hey, let's put a little F here. Find the probability that they add to 7. Oh, you know what? That would be, I'll change colors. I did it in black. That would be that group there. Also, what happens to be 6 out of 36? Yes? What's the probability that they add to 10? I'm not going to circle it, but can you see it? Now, you're going to notice most of the time there's going to be some kind of a pattern. Do you guys notice all the ones that add to 10? Right there. 3 out of 36. That's one reason, Mark, the sample space chart for dice, really handy. There's lots of nice little, hey, I spotted the trend. Mr. Dueck, can we do these without drawing it? Eventually, maybe, but this is our starting point. Okay? So there's our terminology. What's our homework? One is good. Skip 2. 3 is good. Four you might find tricky. It's practice drawing a tree diagram. But already you're going to be able to answer this with a good tree diagram. So it says packet 1 contains an orange candy. Hey, let's use O for orange, L for lemon, and S for strawberry. Package 2 contains an O, an S, and an R. By the way, you may notice we're also using letters. Are you saying we can turn these into words? With a bit of cleverness, we can bring our combinatoric stuff in here as well. See if you can answer number 4. It's a bit tricky, but I think you can handle it. 5 I'm going to pass on. 6 is kind of cool. You may have done this. So how can you flip a coin with 3 people? Everyone flips the coin, and it's odd person out loses. And if it's a 3-way tie, flip again. It's either going to be a 3-way tie or 1 and 2. So a little trick if you ever like 3 of you going out for dinner, I'll flip you for the bill. 3 of you flip a coin. See if you can figure it out. 6. 7 is good. 8 is good. 9 is, see if you can figure it out. 10 and 11. Let me pause this.